Welcome to NASA Edge.
An inside and outside look at all things NASA.
We're broadcasting live from LC-39 just across the water from the Atlas V, which has begun to roll out, carrying the Solar Orbiter spacecraft out to the pad.
You know, Blair, it never gets old seeing an Atlas V roll out to the pad at Complex 41. But I got to tell you, though, it's not very warm here in Florida. It's kind of cold today.
It actually is. But regardless, a very exciting time here on the Space Coast for space exploration and science today.
I tell you what, over the course of the next 30 minutes, we're going to have a lot of content. We're going to be focusing on the Sun, the Solar Orbiter mission, and the Atlas V vehicle. That's
right. And we have a special guest today. Speaking of Tiffany Nail, her brother is going to be filling her shoes out at the pad with Mick Waltman. They're going to talk about the Atlas V and Solar Orbiter as the rollout completes later in the show.
Well, I tell you what, we have a lot to cover, so let's get started, Blair.
Absolutely. We'll go to the pad, and then we'll come back with our first guest, Holly Gilbert.
We're being joined now by Holly Gilbert, who is the Heliophysics Science Division Director at NASA Goddard Space Flight Center and the project scientist for Solar Orbiter. How you doing?
Great, really good.
So give us your thoughts. You see the rollout of the Atlas V vehicle, Solar Orbiter.
It's amazing. It really is. I have goosebumps, to tell you the truth, not just because of the weather, but because of the excitement of the rollout.
Tell us, why is it important for us to study the sun?
Well, of course, the sun provides everything, right? Life here on Earth. But we also are impacted by its moods and its activity. It's incredibly dynamic. We're embedded in basically its atmosphere, its extended atmosphere. So whatever happens on the sun, solar storms, solar wind, it affects us here on the Earth and what we call space weather. And it interacts with the Earth. It can damage satellites. It can be dangerous for astronauts. It can cause power grid outages. So space weather is a very important field to study.
Now, of course, as everyone knows, we are going back to the moon in 2024. We're going to have the first female astronaut to land on the surface. And how is studying the sun sort of impact that journey back to the moon?
Yeah, like I mentioned, so on the surface, we're protected from all that space weather because we have the Earth's magnetic field and the atmosphere. But those astronauts are going to be outside of that shield, right. And especially once they're on the moon, and especially all the way to Mars. So we need to be able to forecast and predict, and we need to understand the fundamental physics processes in order to do that. Our models need us to feed them information. Solar Orbiter will help provide that data to do that.
Now, as project scientist, what is your role in the mission?
I get to do fun stuff like this, but really it's a collaboration, so I work closely with the ESA project scientists as well, and we really oversee the science objectives and make sure that the data is going to accomplish what we're trying to do scientifically, and we work with all the teams, the 10 instrument teams, and so it's a really collaborative effort.
Now, you know, Blair had a chance to sit down and talk with Cesar Garcia, who is the project manager for Solar Orbiter for the European Space Agency. So let's learn more about the Solar Orbiter.
Great.
We're here at Astrotech Space Operation with European Space Agency Project Manager for the Solar Orbiter, Cesar Garcia. Cesar, thanks so much for being here today.
Thanks you for having me.
The first question I want to ask you is, tell us a little bit about the overall mission for Solar Orbiter.
Okay, Solar Orbiter mission, as the name shows, it's a space mission that will orbit around the Sun in ways which we have not done before. We will be different in that we will be relatively close to the Sun, and we will also change the orbital plane so that we can observe the poles of the Sun. We will investigate also the solar wind and features close to the surface of the Sun. Then they will also look into the heliosphere, and we all live in the heliosphere of the Sun. And finally, they will investigate the reasons why we have this 11-year cycle and what drives the solar variability.
Some of the instruments are going to be capturing images. What are those images going to look like?
Well, we capture images in various frequencies across the spectrum. Normally, science instruments, or also Earth observation instruments, they don't take what we call white light pictures. We try to take pictures in a very small frequency band, and then we combine those various frequencies to create broad spectrum images. Now, Solar Orbiter has instruments in the visible, so the various colors of the visible, a little bit in the infrared, also in the ultraviolet spectrum, and all the way up to the X-rays. So the various instruments will detect these images in different ways, and what the scientists do, they combine various frequencies to create, well, pretty pictures like the one we have in the background here. That's one element, and the second element is that the various instruments, they have different fields of view. Some of the instruments will be able to capture the complete solar disk, and at the same time they will be able to look with very high resolution into very small portions of the sun. Some of the instruments will be looking at the rim, or to make things more interesting, when one of the instruments detects a feature of interest, he will send automatically a trigger to the other instruments so that they can also change mode of operation and focus on that specific feature to learn more about it. And if that involves, for instance, the ejection of material or a change to the solar wind, when that happens on the spacecraft, then also the in situ instruments will be able to react and to sense that specific feature. And that combination of things which happen on the surface or close to the surface of the sun, and then at the location, later on at the location of the spacecraft, is one of the key features and unique features of Solar Orbiter.
There are a lot of fascinating and important instruments on the spacecraft. If the scientists see something interesting during an observation, do they have the ability to adapt and sort of reorient to take a look at that interesting event?
Yeah, they want to maximize the opportunities, of course, and there are several ways of doing that. One way is something that we call the short-term planning, as opposed to long-term planning. Long-term planning is what the scientists do. They plan every instrument, every mode of operation, like 6 months in advance. However, every 24 hours, if they see a particular feature, or if there is a signal coming from a different space mission or from the ground, then they can change in very short time what the instruments will be doing in the next observation day.
Joining us now is Teresa Nieves Chinchilla, and she's the Deputy Project Scientist for Solar Orbiter on the NASA side. Thanks for being on the show.
Thank you for
Now, I tell
having
you,
me.
when I talked to Cesar Garcia, he talked a lot about collaboration, and we actually just heard from Holly about this word collaboration. So it seems like, despite being very different missions, a lot of coordination has to take place. So tell me a little bit about your role and how you see this collaboration playing out for Solar Orbiter.
So collaboration within the mission has been very important. This is a very international mission with a lot of countries putting together efforts and energy to accomplish the goals of this mission. So we have also more collaborations. This is very important with, more missions for NASA like Parker or SDO stereo missions. They are very important in our field, and working together we can enhance the outcomes from each mission.
Obviously, Solar Orbiter has 10 instruments. Do you happen to have a favorite on the spacecraft?
It is not good, you asked too much to say my favorite, but I'm heliospheric, so it means that I study the atmosphere of the sun, and I like Solo High because I study large structures and I like to see how they evolve in the heliosphere. I like to track them and later to touch them and to sense them with the in situ instruments. So yeah, but I don't know. I don't have a favorite.
But it's interesting. As a scientist, obviously you gravitate towards certain data, and that's important too, even though we like all instruments. Awesome. Well, I tell you what, thank you so much for coming on the show. We really appreciate it. We're going to shift focus now to the spacecraft itself. I had a chance to sit down with Ian Walters, who's the project manager for Airbus for Solar Orbiter. Let's check it out. We're here at Astrotech Space Operations in Florida with the European Space Agency project manager for the Solar Orbiter spacecraft, Ian Walters. Ian, you're responsible for the entire spacecraft. So tell us, what are the key features of the Solar Orbiter?
Well, I think the one feature that most people will realize is because we're going so close to the sun, we'll need to protect ourselves against that. And the way we do it for this mission is to hide from the sun. We hide behind a heat shield. And the heat shield itself can tolerate the enormous temperatures that we see. We're 42 million kilometers from the sun at the closest approach. It doesn't sound that close to most people, But when you think we're 150 million kilometers here on Earth, it's a lot closer. So we expect to see temperatures around 600 degrees centigrade. Most of the spacecraft can't tolerate that kind of temperature, but the heat shield can. So we design specifically a shield for that purpose, and we hide behind a shield for the entire 10 years of the mission.
I know that other spacecrafts travel close to the sun and require a heat shield, but how do you test a heat shield that has to endure that kind of heat?
It's a good question. So we can't test a spacecraft, the entire spacecraft at 600 degrees. We have to test the components themselves, and then we do an all-up spacecraft test, but at lower temperature. So the heat shield itself has been exposed to those kind of temperatures. We built a bespoke test environment in which we could reach the temperature. So the heat shield has been tested to 600 degrees. Also, the elements that poke out into the solar environment as well. So the solar arrays, for instance, and the high gain antenna, they both also see 600 degree temperatures. So they've also been tested to those temperatures as well.
Now, you said 10-year mission, so it's one thing to tolerate that kind of temperature. How do you test for that amount of time?
Well, we don't test, of course, on the ground for 10 years. We do material level tests, accelerated tests of the materials to show that they can tolerate the full duration of the mission. For instance, we have special coatings. We have something called Embio Black, which is very, very black. I think it's one of the blackest materials we've ever flown in space. And we've made sure that it stays black and it doesn't degrade under the intense radiation environment you find close to the sun. We also have a material called Embio White, very much similar to Embio Black, but white. Problem with white paint is that they can start to go grey under extreme ultraviolet exposure. So we've tested those materials, those coatings, with accelerated tests to show that they will survive the 10 years.
Obviously, the heat shield is a big challenge. You seem to have taken care of that. What are some of the other challenges on this mission? Because you have a lot of instruments on board.
Yes, that's right. We have 10 instruments altogether. 6 of them are what we call remote sensing instruments, so they look at the sun through the heat shield or next to the heat shield. We also have 4 in situ instruments, which measure the environment around the spacecraft, so the local environment. So 10 instruments is a lot. Each has their own unique challenges. Each instrument will bring specific requirements to the spacecraft design, and some of those can be real challenges, real design drivers at spacecraft level. I'll give you one example. We have an extremely sensitive magnetometer on board. It measures the magnetic fields local to the spacecraft in the plasma being emitted from the sun. It's extremely important to measure the magnetic fields around the sun. It seems we don't have yet a very good model of how the sun works in terms of its magnetic fields and so on. And so we're taking a very, very sensitive magnetometer there to find out. Of course, what we don't want to measure is the magnetic field of the spacecraft. So we have to make sure the spacecraft effectively disappears as far as its magnetic field is concerned. How to make a spacecraft out of material which is non-magnetic, it's quite difficult. There are features of the spacecraft that have to use magnets. The reaction wheels, for instance. These are spinning wheels that we use to control the pointing of the spacecraft, which is, as you can imagine, so important that we hide behind the heat shield all the time for 10 years that we don't accidentally depoint from the sun. So those reaction wheels are critical for the mission, but they have spinning magnets inside. We have to make them disappear. So we built a special shield around those reaction wheels made out of mu metal, which is a very strong attenuator of magnetic field. But we couldn't easily measure it. As you know, the Earth's magnetic field is much, much higher than the signal we want to measure. So we have to make the Earth's magnetic field disappear as well in order to measure how effective those shields were. We did it at reaction wheel level. We were sure the shielding would be good. We also get some shielding from the spacecraft components again, but we were looking for an attenuation of a million times less field from the wheels by the time it gets to the magnetometer. Very difficult to test, and in fact we could only test those at spacecraft level in a special chamber in the woods in Germany, which effectively makes the Earth's magnetic field disappear, and then we can really see what signal is coming out of the reaction wheels and can it be measured by the magnetometer. And I'm pleased to say when we did that test last June, we could not see the wheels at all. The shields were completely effective.
Wow.
So this is just one example of how an instrument requirement can have a very strong drive on a spacecraft design.
Hey guys, I'm Daryl, and this is Mick, and you're a vehicle systems engineer with Launch Services Program, and of course behind us, the noise you can hear is the mighty Atlas V, United Launch Alliance's rocket, rolling to the pad as we speak. Mick, we're just about, what, 50, 60 feet away from this thing. It's impressive.
Oh, it's very impressive, Daryl. Happy to be out here for Solar Orbiter. This is great access to be able to see roll to the pad today. The team has done a great job. They've been on time. Everything's looking good. And as you can see, we're just a few seconds away from getting that thing into Launch Complex 41 and prepared to get ready for tomorrow's launch.
Tell me a little bit about the rollout. It started at around 10:15 this morning, and we had probably about 6 football field length trip from the vertical integration facility out here to the pad.
Yeah, it does. The team started early this morning, got preps done inside the vertical integration facility, raising up decks, moving things, changing over the environmental control system from the tower, the VIF, to the mobile launch platform. Then they got rolled out of the pad, like you said, about 10:15. They rolled out of the VIF, started moving. Takes about 15 minutes for them to travel the 1,800 feet from the VIF to the pad. They travel just under 3 miles an hour once they get moving. Really impressive sight to see the mighty Atlas V rolling out here today.
And now we're probably just about, what would you say, 60, 70 feet from being into the pad.
Absolutely, we're very close to them getting everything put down and hooked back up.
And when they get that hooked up, it kind of explains this, because what we're seeing behind us, you can see in the picture, are some railroad tugs that are pushing that mobile launch platform with a rocket on it and pulling its support systems behind it, right? How does it go into the pad there?
Yeah, so the clean pad concept that ULA has for the Atlas V is they roll out of the VIF using tugs pushing the mobile launch platform, like you said. So they don't have a fixed umbilical tower or anything like that. It's a mobile launch platform. They get that moving down the tracks, and put behind the whole setup, they have their environmental control system on a trailer type thing. They get that into the pad, they push the support trailers into the concrete bunkers and get the vehicle and the mobile launch platform over the flame bucket and set it in place, and then they do the hookup from the environmental control system to the pad systems, and then they get the auto couplers for the commodities, the locks and hydrogen fuels for the Atlas vehicle to be able to get everything ready for tomorrow's launch.
Once they get that rocket in there, does the countdown begin, or how does that work?
So actually we've started in what we call the F-1 day count, which is the rollout and everything. Once they get it all in and out, they will actually begin the launch countdown, getting ready for tomorrow's with some built-in holds, several long hour holds, and then picking up the count tomorrow about 6 p.m. The team will come on console and getting everything ready for a launch at 11:03 Eastern Time tomorrow night.
All right, Mick Woltman, Vehicle Systems Engineer with Launch Services Program. We appreciate you. It was impressive to watch this rocket roll right by us just a few feet away. We're going to wrap it up for now and send it back to the guys at the gantry.
Thanks a lot, Daryl. I tell you what, that Atlas V wasn't built here. It took a journey of its own, all the way from Decatur, Alabama. And you had a chance to talk with the captain, Captain John, of the boat that actually transported the Atlas V all the way to Kennedy. Let's check that out.
After years of watching ULA launches, one of my biggest questions was, how do they transport their rockets from their facility in Decatur, Alabama to the Cape? It turns out they have their own boat to do just that. It was cool to see all the inner workings of the ULA rocket ship, and I couldn't wait to learn more from Captain John. Captain John, this is a very impressive ship, but I want to know, how long have you been captain of the rocket ship?
Okay, this is my 9th year captain of the rocket ship. I've worked all the positions as mate to make it to this position, so yeah, 9 years.
So you've had a lot of experience transporting these important payloads such as Atlas boosters and Centaur stages and the like. Is this ship uniquely designed to carry these incredible boosters?
It is. The vessel was drawn up by a naval architect with shallow water in mind. We go places that other commercial vessels of this size cannot go. We have air draft limitations, and then we have wake problems, so they designed the hull that would have minimum effect in shallow water areas. We make a speed in the inland waters roughly about 10 knots. We have about 1,300 miles of rivers to travel. So there's challenges along the way with high river conditions and low river conditions, heavy currents and no currents. We always, in these river trips, we have to take these ever-changing circumstances into account, part of our passage plan.
How do you account for these river changes? Does that affect when you can go pick up a booster, or?
It's a very thorough process. We generate roughly about 40 page document of data that we expect from regulatory agencies, from the mariners that happen to be out there. They do reporting. It gets put into the local notice to mariners. We'll pull that information. We have a meeting with the crew before we sail, and we'll literally review 1,300 miles of river before we ever leave the dock.
Wow. Well, I guess that's important since you're carrying this incredible, important booster or rocket. Got to make sure it gets there safely.
Sure. And we're all aware aboard the rocket ship of how valuable it is to get the flight hardware from Decatur, Alabama, here to Cape Canaveral, Florida. So part of the passage planning, we take into account the value of the cargo, what we have. The weather routing is also very important out at sea. At times we'll have to weather route around a system in order to assure a good ride for the equipment and of course the crew.
Do you ever weather route, say, to the point where you end up at an exotic tropical location like Cozumel or Jamaica or?
I wish.
Well, I mean, like for safety.
Well, seriously, we get into the deep part of the Gulf of Mexico, and usually we may just alter out maybe 50 to 100 miles. We can see things developing. Forecasting is really good compared to 40 years ago. You know, we keep in mind that we're very close to Cuba. If we're weather routing, that we have to keep that in mind. We have to, you know, make sure that we're, you know, keeping a safe space, you know, from Cuba.
What size crew do you have here on the rocket ship?
We have a 16-man crew that's required by the billet set by the Coast Guard. When we're on the rivers, we expand somewhat. We have 2 river advisors. They basically are towboat pilots that have heavy tow experience. So we'll take them aboard and then have an 18-man crew.
So as captain of the rocket ship, do you have to think differently based on the type of payload you're carrying, whether it's like a Delta II or a Delta versus an Atlas or anything of the sort?
Yes, we do. The Delta is more robust. It's a boat down to the deck type of configuration. As opposed to Atlas, Atlas will come on a trailer and will have chains. So you do have to take it into account the method that we're securing the cargo. We want to avoid heavy rolling, so we may alter course and point up a little bit into the seas and alter that rolling and dampen it somewhat. So yes, we do have to take that into consideration.
And what's your record on successfully delivering rockets? Are you like 20-0 or?
We have a perfect record aboard the rocket ship. Just like the flight hardware itself that goes up, we have a perfect record here, and we do get the payload here on time.
So you're basically undefeated.
We are. I don't know the right number on it, but I could say that if we'd made voyage number 133, I made half of them. So I'd say I did about 70 trips.
70-0. That's almost like that's top NBA record.
Slam dunk.
Yeah, that's great.
I tell you what, we had a great show today. We learned a lot about Solar Orbiter, the sun, and of course the Atlas V vehicle. Let's take one last look at the pad. It looks like rollout is just about complete. What a sight to see.
You're watching NASA Edge.
An inside and outside look at all things NASA.
I have spoken.